Started now. So good evening, everyone, and thank you for coming. We are very pleased to have Dr. Bhavik Bakshi here to give his talk on including nature in human decisions for innovation and sustainability in the Anthropocene. I should introduce myself. I'm Subhashish Ghoshal. I'm the director of the Trottier Institute for Sustainability in Engineering and Design. And so there are many seminars that we hold over the year, and we're particularly pleased to host this particular one on LCA and sustainability, a topic that's definitely very important in the field. So to introduce Dr. Bakshi, he is a professor in the Department of Chemical and Biomolecular Engineering at Ohio State University. And he's definitely one of the pioneers in the field of sustainability in engineering systems and life cycle analysis. His research spans, I guess, the two major topics he touches on are sustainability and process systems engineering. Mm-hmm. And Dr. Bakshi's been the recipients of several prestigious awards, and most notably, he was awarded, I want to say the name of the award correctly, so I'll just take a look at my notes. The award for research excellence in sustainable engineering at the American Institute, by the American Institute of Chemical Engineers. And he's got a illustrious list of publications, and one of his publications on the economic impacts of pollination by various animals on economic output of the U.S. was rated as one of the top 2 papers by Environmental Science and Technology. So very interesting body of literature that you've put out over the years. And so I look forward to the seminar, as I'm sure you are. And with that, let's give Dr. Bakshi a very warm welcome.
Okay, thank you. Thank you very much, Professor Ghoshal, for the kind words there. And thank you for attending. I'm actually impressed. End of the day, and people are still here, and hopefully you will stay. So that's very nice. I certainly appreciate the invitation and the opportunity to come to Montreal and to McGill University. It's have had a very nice time interacting mainly with lots of students all day. Very impressive crowd, good interaction, nice discussion, lots of questions. So thank you for all of that. So what I'm going to do now is try and talk a little bit about some of the research that we are doing in the group, although I'm not just going to focus purely on research. I've tried to make this less of a pure research-like seminar where, pardon the description here maybe, but many times I remember as a student, I would have people coming in, to give a seminar, and it would feel like they're talking more about all the things that they've done without necessarily focusing on whether everybody has the needed background. So over the years, what I've figured out is because the work I do tends to be pretty multidisciplinary, the audience also oftentimes tends to be multidisciplinary. And not everybody obviously is familiar with all of the different disciplines that I may end up talking about. So maybe as a result of that, there is sort of a happy sort of a compromise that I hope I have reached. And what I'm going to try and do, therefore, is certainly talk about some of the research that we are doing, but also talk about things that go outside of my traditional comfort zone, but I think are very important from the point of view of sustainability, I guess also from the point of view of innovation, which are issues that are associated with maybe some social and even economic and ethical aspects of some of the things that we are having to grapple with in the world that we live in today. Okay. So don't ask questions that are too hard in those terms. That's what I'm trying to tell you, basically. Well, only partially. Okay, so the title I'm talking about, including nature in human decisions, right? And so I want to start out by just reminding us about, what do human activities depend on? And as, is I think pretty obvious, the things that we depend on are primarily things that we get from nature, so-called ecosystem goods and services. Things like, fish, fertile soil, forests, scenery, pollination services, and so on. So these are things that are primarily driven by solar energy. And our economic activities convert these ecosystem goods and services into economic goods and services. These are things that we spend money to buy and sell. These are things that we mostly tend to take for granted. Okay, we don't really pay money for the hummingbird that might visit your backyard if you're so lucky and pollinate some of the flowers that you might have over there. In addition, importantly, nature also provides the basis for health and emotional well-being. And this is something that is receiving a lot of attention of late, where people are showing that interaction in natural systems really helps in all sorts of ways, things like cardiovascular health and control of depressive symptoms and those sorts of things. These are some of the things that are getting outside of my comfort zone. Nonetheless, these benefits are certainly there. So human activities do depend on nature. There is not a lot of argument usually against that kind of a statement. So the question then, it seems, that is natural, is if our activities depend on nature, do we account for it, for the role of nature in our activities and so on? And I think the answer there is not really. Okay, we do account for nature, but maybe for the few things where we do account for it, it's in a relatively small way. Most ecosystem goods and services are greatly undervalued. Okay, now this area of the world has plenty of water. At least that's the impression I'm coming here with, right? But if there was a scarcity of water, then people would start valuing it much more than if there was plenty of water. Okay, and if you look at the situation in Southern California and southeastern parts of the United States and northwestern parts of Mexico, the situation has been pretty challenging. Okay, and it is not just that part, but many parts of the world. Okay, when water becomes scarce, people suddenly seem to miss it and start wanting to do stuff with making sure that we use it efficiently or we find other sources and so on. So a lot of ecosystem goods and services tend to be valuable when they are either degraded or are really depleted. Okay? Otherwise, we just take it for granted. Okay? Implicitly, the capacity of nature to supply goods and services is oftentimes taken for granted. Right? We expect when we drive by that the CO2 that we are emitting is going to get taken care of. Okay? Now we know that it hasn't been, but we don't know it enough to have enough happening to change that. Okay? Most academic disciplines, in fact, have tended to take nature for granted. Okay? Engineering, the goal of engineering, if you read especially the old literature, all right, from 50 years, 100 years ago, there is a lot written about what is engineering and what is its purpose. Okay? And one of the themes that you will see in there is this thing about controlling and subduing nature, dominating nature. Okay? And there are plenty of examples about that. Thermodynamics. Implicitly, there is this assumption in thermodynamics about an infinite sink. An infinite sink implies that you have a sink where you can put whatever you like. Its basic composition will not change, and its basic conditions will not change. Well, guess what? That infinite sink that we have on the planet, that we have assumed to be infinite on the planet, is actually changing in terms of its composition. Look at the atmosphere. We have 400 parts per million plus of CO2 now. Before the Industrial Revolution, it was closer to 280 parts per million. So that sink itself has been changing. Economics has tended to keep nature outside the market. okay? It treats, ecosystems more as an externality. And this concept of public goods that is there in traditional economics, where these public goods are assumed to be non-rival and non-excludable, which in simpler terms is basically that anybody has or everybody has access to these public goods, okay? And you can use them and they won't necessarily deplete for the other person. And typically public goods are the things that we get from nature, okay? Things like clean air, things like, water and other types of goods and services. Even ethics and philosophy have tended to ignore nature, because the way modern ethics and philosophy have developed over the last couple of centuries, the focus has been mainly on the behavior of people with other people. We have ethics about how should we behave with our neighbors, how should we behave with human rights violations, again about people, right? Clearly important, no doubt, very much needed. But those disciplines also, according to the people who work in this area, they haven't really developed to take into account, or to consider how should people behave with nature. So even there, nature seems to have been, not taken into account as much as maybe it should have, okay? What are the outcomes of ignoring nature? At least two major outcomes as far as I can tell. One is ecological degradation. If we ignore something, then as I was saying earlier, we will realize its importance only after we are running short of it, okay? And exceeding that ecological capacity causes ecological degradation. And there are plenty of examples of that. I was talking about, California and the southeastern part of the United States. Some of you may have visited Hoover Dam. That's what this picture is of, all right? And you can see this white ring here that indicates how low the water level is these days. Okay, this is not a very recent picture. As you can see, it is 2014. And this year, the winter has been relatively good. It has snowed and there has been some rain because of El Nino and other factors. But nonetheless, this problem of water scarcity in that region is there, and nobody is expecting that it's going to go away anytime soon. Okay? So that's an example where we are demanding more from nature than what it can supply, and that's what leads to depletion and degradation. Another example, so I came here from Mexico. I was at a conference in Puerto Vallarta, which is on the Pacific Ocean, beautiful place, etc. So this picture is not from there. This is Mexico City. Okay, but air pollution is an issue. Mexico City is an example. New Delhi is an example. I spent 2 years living in New Delhi until about 2012. Beijing is an example. Los Angeles used to be an example, and so on. So one way of thinking about air pollution is that we are emitting so much into the atmosphere that natural systems that have an ability to clean up the air are overwhelmed. They can't clean it up anymore, and so we get the waste becomes pollution and can have a harmful impact. This is from a little bit closer to here, I guess, and closer for me, closer to home. This is Lake Erie, okay? And here you can see Lake Erie. If you look at it in this region, it's pretty clear. Over here, there's lots of algae. Harmful algal blooms have been a problem in that lake and many other bodies of water, both fresh as well as salt water. The Gulf of Mexico has a huge dead zone that appears every year. And again, this is because the natural ability of the lake and the surrounding wetlands that used to be present around Lake Erie, this area out down here used to be what was called the Black Swamp, which was drained about 150 years ago and is mostly gone now. Okay? But nonetheless, the emission of nitrogen and phosphorus runoff that is going into the lake is more than the natural ability of the lake to clean the water. And that's why we get these harmful algal blooms. And Toledo, which is located approximately here, did not have drinking water last year for several days, like 4 or 5 days of the week, which had never happened before. So it's affecting human well-being. This is the famous Keeling curve that you may have seen. I mentioned CO2 earlier. This is the concentration of CO2 in the atmosphere over the last roughly 300 years. And it has been increasing pretty much exponentially more recently. And this is also because we are demanding more from nature in terms of carbon sequestration ecosystem service than nature is able to provide. Okay, and that's why we have the increase in atmospheric carbon dioxide. So this is a figure that has become fairly popular in the environmental sciences sort of community, and some of you may have seen this before, in addition to some of the previous graphs I showed. So this is basically talking about various ecosystem services that we get. And the green indicates what these scientists have called the safe operating zone for humanity. So if this is yellow, it means that it is outside the safe operating zone. We are getting into a risky situation. We are demanding more from nature than nature is able to supply. If it is red, we are way outside. This is really, very highly risky kind of a situation. And as you can see, as far as biodiversity loss or biosphere integrity is concerned, we are off the charts. Okay? As far as biogeochemical flows are concerned, this is for nitrogen, this is for phosphorus. Also, things are pretty serious. Climate change or carbon cycle is not quite red yet, although it's pretty close to that. It's getting that way. All right? So even from a global, this is a global perspective here. It's planetary boundaries, right? So even from a global perspective, we have been exceeding nature's capacity to supply goods and services that we need for our own well-being. This cartoon came out a few years ago, and I think it really captures the dilemma that we face today, right? So you can see development of man, if I may put it that way, but it is relying on the very planet that we live on. Can this be sustained, right? Okay, the other disadvantage of ignoring nature is missed opportunities for innovation, all right? And what I mean by that is, based on the fact that, nature is able to provide all sorts of services that we do benefit from, all right? So if we ignore nature, this ability of ecosystems to satisfy human needs may not be discovered. We may not find them. We may not include them in our thinking and our designs and our decisions. So wetlands, as you may know, provide all sorts of ecosystem services. They have the amazing ability to remove all kinds of pollutants from water, ranging from sewage and solvents to pesticides, excessive nitrogen, phosphorus, and so on. And they're able to provide, fresh water, food, biomass, flood regulation types of ecosystem services, and so on. Trees, as I'm sure everybody knows, they take up CO2. But trees also take up other pollutants like particulate matter, nitrogen and sulfur oxides, and so on. And they provide, of course, oxygen that we need to survive, home for pollinators, fuels, but also recreational and aesthetic types of opportunities, right? So the point is that if we ignore the ability of nature to provide us these kinds of goods and services, then maybe we are missing out on ways of working with nature that could be beneficial to us, all right? So one question that may come to your mind is, okay, so if nature is doing all these things for us and if things are in this kind of a situation, well, is the contribution from nature really significant? Or maybe it is so small and that is why nobody has really, bothered about this, at least, more recently. So here I've tried to collect a few examples of the contribution from nature to try and convince you that yes, the contribution from nature can be truly significant, okay? So one estimate about carbon sequestration by restoration and management of soils and forests is that we can reduce atmospheric CO2 concentration by 50 parts per million over the next 50 years. Now 50 ppm is a big number, right? We are at about 400, okay? This would bring it down to 350, and it would satisfy a lot of the targets that people are talking about these days, right? Of course, it will take time, okay? But we need all solutions at this point. It's not like, oh, this is going to take time, so forget about that. We don't have that luxury, in my opinion. Insect pollinators are estimated to contribute $200 billion to global agriculture. Now, that's a big number, right? If you like citrus, you like almonds, right? Melons, etc. They need pollinators, okay? And I believe monarch butterflies make it all the way here in the summers, and I don't know what their population is, but I I'm almost certain that their populations have plummeted. They've plummeted everywhere in the world, everywhere in North America, basically, which is their domain. Restoration of natural vegetation, these are results that we have found, and I will show you a slide on this shortly. So restoration of natural vegetation could mitigate all of these sulfur dioxide emissions in a cost-effective manner in more than 15% of the US counties. Okay? So a lot of companies are talking about going to zero emissions now. That's the new thing. They want net positive impact manufacturing. Okay? So they don't want to just go to zero. They want to do better than that. That's the marketing type of buzzword out there these days. Okay? So I will show you that that is possible in 15% of US counties in a cost-effective manner. That's not a small number. Okay? From the human health point of view, as I mentioned earlier, living close to nature has been shown through scientific studies to reduce overall mortality, cardiovascular disease, depressive symptoms, and allergies. So this is important from a health perspective, to everybody pretty much. And the monetary value of ecosystem services has been estimated to be in the trillions of dollars. Right? So this contribution is significant. If we ignore it, we do it, at our own peril. So why do we ignore nature then? I know chemical engineers don't get taught ecology. Okay, civil and environmental engineering, they have a better sense of environmental and ecological sorts of things, but still, not necessarily. Except for ecology, everybody seems to ignore nature. Okay? So I think the reason why we tend to ignore nature is because a lot of these disciplines developed when the world was relatively empty. Okay, 100 years or 50, 100, 200, 300 years ago, when a lot of the basics of economics, Adam Smith came up with his famous book in around 1776. It's a long time ago. Okay? A lot of the basics of thermodynamics were developed in the 1700s and 1800s. Right? A lot of the ethics and those kinds of principles were also developed roughly around the 1800s and so on. Right? At that time, human activity was a relatively small part of the overall biosphere. And there was a lot of nature, and it felt like, nature is infinite. So assuming an infinite sink was convenient, obviously, okay, for the theory, but it also seemed to make sense because nature was, quite significant, and nobody could imagine that we could become so dominant that nature would become the small thing and our footprint would become much more significant. Okay? So I think there is a good reason why a lot of disciplines have developed in this way. It made sense at that time. But does it make sense today? And a lot of geologists and other scientists are arguing that we are in what they are calling the Anthropocene, which is, according to these geologists, a new geological epoch. Okay? After the Ice Age, we were in the Holocene, and we are. Officially, they have not accepted the Anthropocene yet. There is a committee that is looking into it, and all these decisions seem to get made by committee, and the result is expected at any time. But the point is that their argument is that human impact is so large now that centuries from now, if people look back, they will find our signature in geological records. Okay, so that's why they're saying this is a geological epoch. All right. So what we have been trying to do in our research is trying to develop methods and frameworks by which we can include nature in engineering. We are engineers, so we are focusing on engineering. And what we are trying to do, and what I will talk about, is we are focusing on ways by which we can assess nature's capacity to satisfy industrial needs. Okay? And we are developing ways by which we can design integrated networks of technological and ecological systems. All right? And we are also looking at considering ecosystems at larger scales, what we are calling from process to planet, because we don't want to end up in a situation where we take nature into account and come up with a solution that seems to work at a small scale, but all it does is really shift the problem outside the boundary, okay? And ends up in unintended harm and unexpected consequences. We don't want to do that, right? So we have to take a systems view that considers the effect at small scales, but also at larger scales. Okay, and this is obviously not none of these problems are trivial, I think, but the larger the scale, the more challenging it gets. Okay? So what I want to do in the next several slides then is talk about this framework that we are developing that we are calling Techno-ecological synergy, or TES for short, where the intention, as I said, is to include nature's capacity. So I will talk about ways by which we can account for the demand and supply of ecosystem services, the things that we get from nature, and ways by which we can encourage synergies between technological and ecological systems, and also consider systems at multiple scales. All right? There is other work that we are also doing, which I'm not going to really spend much time on, but we have another framework that we are developing that we are calling Process to Planet, where we are able to integrate detailed engineering models, which can be nonlinear, they can be dynamic, with life cycle assessment and economic models, and the economic models we are considering tend to be linear and empirical, and the life cycle models are certainly linear and empirical. And this framework, we're able to then use it for so-called sustainable product and process design. That's where our focus has been primarily. So this integrated framework, this is at a small scale, this is at an intermediate kind of a spatial scale, and this is at a large aggregated, coarse spatial scale. So if we use this in a bottom-up manner, then we can use it for sustainable product and process design and those kinds of tasks. If we use it in a top-down manner, which is something that we are working on right now, we believe we can use this framework for figuring out what might be the effect of an economic policy, like, say, carbon trading, on individual industrial processes or corporate types of activities, and so on. Okay, so that's also work in progress. I'm not really going to focus on this in today's talk. Okay, so this techno-ecological synergy, the basic idea, I'm going to convey it to you through this one slide. So as you know, if we have technological systems or broadly human activities, we need raw materials, we make desired products, and we produce wastes, right? Now, obviously, a lot of activities, there is a lot of effort to try and minimize the production of waste, okay? Great things must be done, improve efficiency, and so on. Wonderful things to do, plenty of work on that in traditional engineering and other areas associated with this. There is also effort on trying to actually close this loop, meaning use wastes as resources. Okay, so earlier today we were talking about this for the students who are here. These are ideas like industrial symbiosis or byproduct synergy, and now the buzzword lately is circular economy. Okay, where the intention is that wastes from one process should be used as resources in another process. So ash from coal burning power plants should be used to make maybe roads or go into concrete and so on. Okay. So this is also certainly worth doing. A lot of activity, these are some of the names that are being used for such activity. Traditionally, these activities do not account for ecosystems. So what we are trying to do is to include the role of ecological systems and take into account the fact that some of these wastes can be taken up by ecosystems, as I showed on the slide with the wetland and the forest systems, and they can produce resources that can then be used by technological systems. So what we would like to do is to establish better linking between technological and ecological systems, okay? And that's what we mean when we talk about synergy. Ideally, and I agree this is utopian, all right, but ideally, maybe what we should aim towards is a system that is not like this, but is like this. So notice the difference is that here we have raw materials and pollutants, but now we don't have those, meaning everything gets used by nature or by technological systems, and whatever the technological systems need or human activities need comes either from nature or from other technological systems. So try to really emulate the way ecosystems tend to work and the way they are able to sustain themselves. Okay? We are obviously nowhere close to this, but one has to aim for the moon if you want to get anywhere. That's sort of the thinking here. All right? Okay. So how do we go about doing these sorts of things? I'm going to introduce some little bit of jargon and some terminology now that I will use then in the examples that I'm going to provide. Not a lot of jargon, just a little bit before I get into applications and make sure I keep track of the time here. Okay. So we're going to talk about ecosystem services and specifically the demand and supply of ecosystem services. So what do we mean by that? Right? So some examples here. So let's say our ecosystem service is carbon sequestration. So the demand from human activities for the carbon sequestration ecosystem service can be quantified by the CO2 that is emitted by the human activity. Okay, because the CO2 that is emitted, one can think of that as, we're emitting it into the atmosphere, which means that we're expecting that it will get sequestered by nature. So that's the demand for the carbon sequestration ecosystem service. What is the supply of that carbon sequestration ecosystem service? Well, that depends on the ecosystems that are available to take up that CO2. Depends on the local forests, the local soil management, local agro ecosystems, and they don't have to be local. A molecule of CO2 emitted here could be taken up in Angola, and that is fine. So the largest scale of this service shed is global. CO2 has global reach, can be taken up anywhere on the planet, and that is fine. All right? If you think about water or water provisioning ecosystem service, the demand for the water provisioning ecosystem service can be quantified by the water that is withdrawn for that particular human activity. All right? The supply, well, that depends on the renewable water that is available from rivers, aquifers, etc. And the largest relevant scale of that service shed is the watershed. Okay? If you think about, say, pollination, the demand can be quantified by the flowers that need pollination to get the desired, or not the desired, but the natural yield from that particular type of plant. And the supply is basically the availability of pollinators, bees, hummingbirds, butterflies, whatever the pollinators that are relevant over here are. Here the service shed is very small, it's local. Pollinators don't travel very far, right? So it's going to be probably several meters, several kilometers. Okay? All right. Yeah?
What do you mean by watershed?
So by watershed, I basically, it's a traditional sort of a definition of the watershed, which is the region where, if the water falls in that region, it's going to go into that particular river, let's say, right? So it's just that region which is the catchment area, effectively, of the river or the body of water that we are considering as the source of the water. Okay? All right, sure. Okay, so now what I'm going to do is show you a couple of examples. I'm skipping all the theory and all that. If you're interested, you can find the papers and all that, but okay. What I'm going to do is show you two examples. One is that of a house. Typical house, I should say North American house, okay, single family home. And then the other example is going to be more of a manufacturing process, all right? So in a typical single family home, what we are thinking is of technological, okay, so sorry, I should back up. The goal here is we want to live in the most environmentally friendly manner possible, all right? And the house I'm going to show you is a house that my grad student used to live in before he graduated and moved on to the so-called real world, okay? And what he did was he considered technological options that he could use, which are maybe high efficiency appliances, maybe solar energy through photovoltaic panels, through solar hot water heaters, use better insulation, and several other technological options, okay? More efficient faucets, etc., etc. Okay? Ecological options were the possibilities in the yard, which he could control. He didn't look beyond that. So it would be a matter of planting trees in the yard, around the house, at other places. What kind of turf he has? Does he have a regular lawn, which is very common in Ohio? Or does he replace it with native plants? Does he grow vegetables? What does he do? All right? And maybe he has a little rainwater harvesting system, or maybe even a treatment wetland for the waste. It's not allowed in the region where he was living, but it's a simulated example. So he did consider that. Okay? And very importantly, he also considered behavioral options, which is where is the set point of the thermostat kept at in the summer and the winter. Okay? And the range that was allowed for the thermostat was not based on what his wife was telling him. He was telling me that. They always debate about that, or quarrel is the word that he had used. But it was based on what the American Society for Heating, Refrigeration, and Air Conditioning, ASHRAE, considers as comfortable range. Okay? All right. So what he found then, so he set up a big model of all this. So the house model he built was using Energy Plus, which is a software available from the Department of Energy, very sophisticated. And we used ecological models for this, and these were just alternatives that we considered for the set points. And what he did was he looked at designing a house with these technological, ecological, behavioral variables that would minimize CO2 emissions, minimize water use, minimize cost. Okay, and I'm going to show you only one result, which is for minimizing CO2 emissions. And what he found, so this is his house. Okay, that's what he told me. I never went and checked it out. About 2,000 square feet. Okay, and what he found is that for minimizing CO2, it makes sense to have lots of trees in your yard. Okay, it made sense to have trees around your house because they would provide shade that would help in the summer, and they would also be good in the winter because it would provide insulation and cut the velocity of the cold wind. Okay, so that's useful both in summer and winter. He found that high efficiency appliances made sense, low flow faucets made sense, highest possible insulation in the wall and in the ceiling made sense. Solar photovoltaics and solar hot water heater made sense, a cool roof made sense. Putting some vegetables made sense. Rainwater harvesting did not make sense from a CO2 point of view because he assumed that we would have to pump the water, and pumping this is all coal-based electricity around there. Okay, so that did not make a lot of sense. And he considered other scenarios. The thing I want to highlight though is that the things that are there in red over here, if you can see it, were the options that were good from all objectives, meaning high efficiency appliances, high insulation, trees, especially around the house, and the highest comfortable thermostat set point in the summer, the lowest comfortable thermostat set point in the winter, were good from every objective's point of view. They saved money, they saved CO2, they saved water. Okay? If you take a traditional technological point of view, the focus tends to be primarily on these. And a lot of green buildings literature tends to talk about a lot of different technological alternatives and not necessarily look at trees, and the behavioral part also doesn't necessarily get looked at. But if you look at all of these three together, what we found is that there are solutions we can find that you can't find if you just look at one of these three categories by itself. Okay? So there are win-win possibilities over here, it seems. Okay. So then we said, well, let's look at now a more industrial-oriented system. So this is now a manufacturing site outside of Cincinnati, Ohio. It's a process that makes biodiesel from soybean oil. Okay? And it also has a combined heat and power plant to generate electricity and heat that is being used in this process. Okay? And what we said is that, so by the way, this is the Ohio River, if you're familiar with that geography. So here is Ohio, here is Kentucky. And what we said is that, so the emissions coming out from this manufacturing facility, these guys also own this land, which is not being used for anything. So what if we planted trees here and we had a treatment wetland over here? Would the ecosystem services that we get from those trees and from that wetland be adequate to meet the needs of this company, of this industry? Or would the contribution from nature be so small that these ecosystem services, yeah, it worked in that house system, but the house has very small demands, right? This is now industrial. Demand is much higher. They're burning coal here. Okay? They're producing industrial type wastewater. So would this be adequate or would it not? That was the question we looked at in this example. Okay? If it did not make sense, then we should forget this line of research. The fact that I'm talking about it means that it did make sense. I'll show you that. Okay? All right. So for those of you who may be chemical engineers here, just to make sure that I'm also a card-carrying chemical engineer, here's a typical process flow sheet. Okay, lots of things happening over here. Don't need to worry about any details. All right. More importantly, these are the emissions from that facility. Okay? So you can see NO2, ozone, particulate matter, sulfur dioxide. These are the criteria air pollutants. Here is carbon dioxide being emitted, and here is the water that is being used in that facility. Okay? Now, traditionally, a company that wants to become more environmentally friendly, what are they going to do? They are going to try to reduce these emissions, right? How are they going to try to do that? Well, they may replace the coal by natural gas, okay? Because natural gas will emit less CO2. They will try to make their process, more efficient, okay? maybe put in some filtering equipment to reduce the particulate matter that is going out, and other things. Okay? Now, certainly these things are important, they must be done, no doubt. But they will not consider the role of ecological systems, the role of nature. All right? So that capacity of nature is essentially not considered in most of these kinds of situations, or all, as far as I know, such situations. Okay, so we said, as I indicated, so if we had the forest here and the wetland here, how much service would they be able to provide? Would they be able to take up these emissions? And to what extent? Okay. Also, would it be cost effective? That's another question that we answered. All right, so let's move on. So what we did was we included our wetland and our forest as if it was part of our flow sheet. Okay? Again, for the chemical engineers in here, we thought of the wetland and the forest as a unit operation, just like you would think of a reactor or a distillation column or a heat exchanger as a part of your manufacturing process. All right? Okay. The goal is to achieve zero emissions from this site. That was our goal. That's what a lot of companies want to do today. All right? We also assume that environmental regulations are already being satisfied by traditional equipment and traditional methods. Okay, because that is the way things tend to be today. Okay, companies in the United States and Canada, I'm sure, and most parts of the world will satisfy the basic regulations. We want to go beyond that. Okay. All right. So here's details about modeling for the ecological systems. If you're familiar with forestry models, we used U4C and U4D models. We used a wetland model, a lot of local information, geography, weather, etc. was incorporated in here. We had help from ecologists on this part. This is not our forte, but we had very good collaboration with ecologists over here, which I'll acknowledge at the end. Okay, so what did we find? So these are the emissions as I showed you, and this is water use. If we had 15-year-old trees, all right, this is the amount of NO2 those 15-year-old trees would be able to take up. You see, the trees can take up more NO2 than is being emitted, and the trees are only 15 years old. It's pretty young, small trees, relatively speaking. All right? In terms of particulate matter, again, the 15-year-old trees can take up all of the particulate matter that is being emitted from this site. If you look at some of the other emissions, ozone, sulfur dioxide, well, not quite. The trees don't quite do the job. CO2, pretty bad. Right? Water, maybe half the water it can provide by recharging the aquifer and reducing runoff and things like that. Okay? But these are 15-year-old trees. What if the trees were older? Then what? Well, if the trees were 15 years old, that's the darker shade of green. The little, this is the shade of green. If they were 20 years old, it is this shade of green up to here. So you see the 20-year-old trees can take up all of the ozone that is going to get produced by volatile organic chemical emissions over there. They can also take up all of the SO2 that is being emitted over the 20-year-old trees. Okay? If the trees were 50 years old, then it is the top of the green bar. They can take up 80% of the CO2 that is emitted from that one site. Okay? And supply 80% of the water that the facility needs. And of course, it will have excess capacity when it comes to these criteria air pollutants. So not only can those trees take up the particulate matter being emitted from that site, they can even take it up from the truck that just went by and the other traffic in the city of Cincinnati and other industry that is around there. So they can provide these ecosystem services to society at large. This is net positive manufacturing. That's the buzzword, as I mentioned to you out there. Maybe it is possible with this kind of an approach. So, does this make economic sense? Physically, it seems to make sense, right? What about economically? Well, here is cost analysis. So what we did here is we considered the cost of the ecosystem. We did take the cost of the land into account and planting the trees, managing them, etc. These are 10-year-old trees, by the way. And here is the cost of the equipment that will do the same job as the trees. The equipment costs more. This is annualized cost. Equipment costs more than ecological solutions here. This is the 10-year-old trees, as I said. If the trees were older, 20 years old, notice the gap is even larger. How come? Over a 20-year period, trees become cheaper. and technology remains the same or becomes more expensive? How come? When you plant a tree and it's growing and everything is set, over time it grows. It can take up even more pollution as it grows, right? Your equipment will decay. So nature appreciates over time, technology depreciates over time. Right? That is why this gap is larger. All right? So, even we did a return on investment and other calculations, and in general, even economically, this looks attractive. Okay, now obviously this is a simulation at this point, but it's just trying to come up with a proof of concept. Okay. All right, so, maybe we got lucky. Maybe we selected one site and it worked, but that was just fluke. So we said, let's look at the entire country. All right, so we went to the US EPA database, 80,000 emission point sources of emission, sulfur dioxide in this case, but we looked at PM10, NO2, etc. And we said, all right, so what we're going to do is we're going to consider the point source of emission, and we're going to consider a 500-meter boundary around that. It's a little bit arbitrary, but 500 meters is not very large. A lot of companies have much more land than just 500 meters. So we looked at 500-meter boundary, and we said we're going to look at the vegetation within that 500-meter boundary. We're going to look at the existing vegetation and see whether it has the capacity to take up the SO2 that is being emitted from that point source. And so those are going to be indicated in orange dots. I'm about to show you a graph here. And those regions or those point sources where restoration of vegetation within the 500-meter boundary, natural vegetation, things that are naturally grown in that area. If it is Nevada, it is more desert-like vegetation. If it is, Maine, it is more vegetation maybe like here. Okay, so we're not doing any genetic engineering and planting, plantations and those kind of things. They're natural vegetation. Okay, so what we found is this. The orange dots, there is enough vegetation even right now to take up the SO2 emissions from those point sources. The yellow dots are the areas, are the point sources where if the natural vegetation was restored, within 500 meters, it could take up the SO2 emissions from these sites. And honestly, these results surprised us. Okay, that there are so many places where just restoring ecosystems could make that particular source, for all practical purposes, zero SO2. Okay? All right, so let me move on. So this is all just analysis, right? We said, all right, here is a site and what can nature do if it was restored? So then we went a step further, and I'm going to speed up a little bit now because the main points have been made. Now this is getting a little bit more sort of engineering design oriented, so I don't want to, I'm not going to get into too many details here. But now by the way, thinking about ecosystems, like wetlands within an industrial context is not new. You may know of companies that use treatment wetlands. All right, there may be people here who are even doing research on that. Okay, it's quite popular. But most of these uses of wetlands, which is the most popular green infrastructure, it seems, these days industrially, most of those treat the wetlands as end of pipe. They don't actually do an integrated design where the manufacturing and the wetland are designed together. I know that for a fact because I don't know of any chemical engineering department that teaches students about wetland design. They teach about reactors and distillation columns and all that, but not about wetlands. So they don't know how to design these things together. There are no simulation tools, no packages, nothing available for doing integrated design, right? So if we do integrated design, then we can find better solutions that are potentially win-win. If we want to use wetlands and trees, we would need to modify our manufacturing processes so that they don't produce so much pollution that they will overwhelm the natural system. Got to be careful about that, right? There are limits to how much nature can handle, okay? So we may need to spend more money on the technology and make it cleaner, but then nature can handle it. And overall, that solution is likely to be economically and ecologically more attractive than what you would get just by a traditional technocentric approach, okay? All right, so what we have found, I'm not going to get into details of anything here. We have applied this to 4 cases. One is biodiesel manufacturing. I just was talking about that same system, but now we are actually doing design. So we're solving this big optimization problem here. We have looked at management of biosolids in Central Ohio. This is a real project with real data, all that, in Central Ohio for managing biosolids to minimize cost and minimize CO2 emissions. Okay, the former mayor was very environmentally oriented, the current one isn't. Okay, but anyway. And then the single family home and yard, I talked about the referential system example, same one. And we've also looked at design of agricultural landscapes, where we are trying to sort of design agro ecosystems for minimizing CO2 emissions and for maximizing profit from there. Okay? All right, but I'm not going to get into any details. What we are finding, so here is a Pareto curve for any system of this type. There are two objectives: one to minimize cost, minimize environmental impact. Conventional designs tend to be to the right and the top of this curve. This area is not reachable. Okay? If you take a traditional technocentric approach, you would end up with a curve of this type. Okay? So, this is the region where you're likely to find your designs, and if you're on the curve, that's optimal. What we are finding is that if you include ecosystems in your design, the Pareto curve moves down and to the left. And we are finding this new design space that is potentially win-win. So for example, think about a point over here. It has lower cost and lower environmental impact. So this is now a new design space that seems to appear if we take the role of ecological systems into account, if we include those in our design. This, to me, is innovation. We're expanding the design space, right? And this design space, you cannot find it if you take a traditional technocentric point of view. Okay? All right. Now, this is, as I told you, this is all simulation, and these are all, very early results. There is no practical application of this yet. There are no tools to do these kinds of things, but that's the fun time to be involved in this kind of research, I think. So, anyway, all right. At multiple scales, I'm going to really go through this very quickly because I do want to leave enough time. At multiple scales, we have basically looked at, say we have a process, this could be your manufacturing process. We look at the local ecosystem. You have a second manufacturing process and a local ecosystem, but that is within a region, right? So something like CO2 can be taken up locally, but it can be taken up regionally as well. Or it can be taken up nationally, it can be taken up globally. From the company's point of view, or from a country's point of view for that matter, which scale is most appropriate for taking up the CO2? Should you build your house so that your house is zero CO2? Or is it better that you, help restore some ecological system in your region so that it can take up some of the CO2 and you get credit for it? Or should you do something like that in some other part of the country or the world? Okay, that's a practical question that comes up when we start thinking about larger scales. And I'm not going to get into any details about that. I'll just show you one slide, one example on this, and then move towards finishing up. So, if we do life cycle assessment that some of you may be familiar with, so here we are comparing no-till farming with conventional farming for corn, okay? If you just consider the emissions of CO2, which is what traditional LCA would tend to do, you find that there is more emission in no-till farming than in conventional farming. So no-till farming, purely from a CO2 emissions point of view, doesn't look that great, okay? But this is only considering the demand of ecosystem services. If you also consider the supply, how much CO2 can the farm sequester, then we get these dark green bars. And you see, no-till farming sequesters much more CO2 than farming with till. And overall, this improvement is much better than this one. So if you consider the demand and supply of ecosystem services, then you will find results that may be counter to what traditional sustainability assessment methods might provide you with. Okay? Now, this indicates that this kind of farming, both of these, can be locally sustainable, right? Because locally, the supply of CO2 sequestration is greater than the demand. But sustainability is a global property, okay? And globally, though, it is still not sustainable because we are still emitting much more CO2 than nature can take up on the larger scale, all right? Anyway, let me move on. And we have a larger system here. So it seems that there are plenty of benefits of this techno-ecological synergy idea, of including nature in human decisions, right? Maybe it will lead to human activities that respect and account for nature. It seems like there are win-win solutions that are possible, okay? And we may be able to come up with definitions that are absolute sustainability as opposed to relative sustainability, okay? Not just this is better than that, but this is really now compared with the basis is how much can nature provide and how much are we demanding from it. But plenty of barriers, lots of technical barriers. Imagine operating a manufacturing process with trees as a part of your system. The trees in the winter will shed their leaves. Now what? Well, that's a challenge. It can be overcome, I think. You have to plant a mixture of evergreen and deciduous trees. And there are possible ways over there. I just want to leave it at that. Plenty of economic barriers. Those trees, in the current market system that we follow, a dead tree is worth more than a living tree. So a company, wouldn't really benefit from having those trees because there is no economic benefit, and the US EPA at least isn't going to give them any credit for it. So why would they bother? Educational challenges. Ecological literacy has an inverse correlation with increasing prosperity. People become richer, then ecological literacy goes down. So we are talking of including nature, but we know less and less about nature. So how are we going to do it? Lastly is behavioral attitude of dominating nature to respecting nature. I think this is happening. All of these things are kind of happening slowly but surely. Three very quick examples of that. So one thing that is happening in economics is this idea of payment for ecosystem services. So there are schemes coming up. In Ohio, for example, there is a scheme where nutrients are being traded. American Electric Power, which burns coal to generate electricity, emits nitrogen oxides. They can't reduce their emissions without costing a lot, so they're paying farmers who can reduce their emissions. Okay? So that is, they're essentially trading nitrogen, the nutrients, nitrogen in this particular case. Okay? Ecological literacy, I already mentioned this. This is from a survey that was done by a group in the United Kingdom, where they showed this inverse correlation. As societies become, human development index increases, GDP goes up, ecological literacy goes down. Okay? And lastly, from dominating to respecting nature, how does this happen? Well, it seems like this is where ethics and philosophy also need to play a role. And here is a quote from this book that I've been reading, and what they're saying is scientists provide factual information. That's what we are good at. But that is not enough to encourage action in society. And what these philosophers are arguing is that we need moral convictions and ideas about what it is to act rightly in the world, what is to be good or just, and the determination to do what is right. Facts and moral convictions together can help us understand what we ought to do, something neither alone can do. So they are arguing that yes, we need the science, engineering, and the facts, but then we also need the moral convictions to actually convert it into action. How do we do that? Well, no dearth of challenges here. As I said, ethics and philosophy have also ignored nature. They have had little regard for non-human world, but this is a very active area of research among philosophers and ethicists and religion scholars also all over the world. So religion also may be able to play a role in mobilizing moral action. All right, so to summarize then, as I said, most disciplines have taken nature for granted, it seems. Ecological degradation and lost opportunities for innovation seem to be two outcomes of that. This idea of techno-ecological synergy can potentially assess and encourage mutually beneficial synergies, maybe provide innovative solutions. It would encourage the traditional technological efficiency improvement, but also restoration of ecological systems and protection of ecological systems. And shift gradually the paradigm from ignoring nature to one where we do take nature into account in our decisions and so on. This requires transdisciplinary research. This doesn't fit in any single discipline, okay? But I think if such disciplinary teams can be set up, I think there are lots of really interesting, really exciting opportunities for pushing the frontiers in this kind of an area. I'm not going to go through this, but lots of people to acknowledge, several students and postdocs, collaborators, specifically Satoshi Hirabayashi and from the USDA Forest Service. He's an ecologist. Guy Ziv from the University of Leeds, who is a physicist turned ecologist and now a geographer. Various funding agencies and several companies who have shown a lot of interest in this work, and we are trying to apply this to some of the sites that they have. And thank you for your attention. If you have questions, comments, I'm more than happy to answer them. Thank you.